Department to give the welcome address.
So welcome one and all join to this wonderful webinar on this day. By the blessings of our founder chairman, Shri P.K. sir, we are very happy to organize various webinars in this pandemic situation. This occasion, I welcome our chairman and managing trustee, Advocate Dr. P.K. sir, in absentia. Welcome our beloved CEO and secretary, Dr. P. Krishnakumar sir, in his absentia. I am happy to welcome our principal, Dr. P. Maniarsan sir, in his absentia. And the chief guest of the day, Dr. Murthy SSS Chavali, Professor of Analytical Chemistry and Nanotechnology, Field Scientist, NTRC, MCETRC, Andhra Pradesh, a visiting professor for 9 universities abroad, and a consultant. Sir, welcome you, sir, for this wonderful webinar, for joining us.
Thank you.
And I am happy to welcome our director, A. Sankaran, sir. Sir, welcome you, sir, for this program.
Namaskar.
And I'm very happy to welcome all the deans, directors, HODs of NIET and other NGA group of institutions to this webinar. I am very happy to welcome all the coordinators, our department colleagues, and the coordinator of this program, Professor R. Kaushik Kumar, for this webinar. Welcome you all. And last not but the least, our dear students who are actively participating in all the webinars in this situation, because every program is for your future and for the growth. So I welcome you all once again. Thank you.
Thank you, sir, for welcoming everyone. Now I invite Dr. A. Shankaran, Director of Aeronautical Department, the presidential address.
Very good afternoon to one and all present here. It's a great pleasure to have the presidential address on behalf of the management, principal, HOD, Aero, other learned professors from my department, and my student friends. It's a really, I'm really fortunate to have today's chief guest, Professor Technocrat. I should start from Technocrat, Professor Dr. Murthy is the right way. Generally, in my experience, I found one or two will be available, like ISRO scientist, or later on become a professor or doctorate. But I've seen today's chief guest is somewhere else. The sense, the topic itself, its topic is not only smart materials. It was a very smart enough within a short span of 3 decades. Almost rather a scaled Mount Everest, and particularly the field of nanotechnology with this basic lab and as a chemistry major. So our days, I remember, talking about way back 30 years back, chemistry, nobody used to go hard for it. We all used to opt for engineering because the balance equation, then titration, then followed by the volume of the work the chemical engineer used to do is much more. So we need to skip up. Although I had a very good professor in St. Xavier's in my college time. But today only I understood the laborious work what they do in our days in PUC, they call it. And one of my friend, senior, he did the chemistry and he joined in ISRO. Later on, he's retired as a scientist because enormous growth for people who have passion only, not only passion but the hard work. As him now also he is in a position to produce more than 20 PhDs and whatnot. I'm sorry if I start talking about professor, time will go off. But I have few words. He struggled hard when aerospace material was introduced, talking about 22 years back. Why at that time, Professor Lalit Gupta also not written any much book. Only CGK Nair, I'm sorry, Dr. CGK Nair presently is there in Bangalore. He's about 80. His book, his experience, he's basically a metallurgist. So those books only is a Bible for me, to be honest. Some 20 years back. Otherwise, no head and tail. Although I have a background from different services, but there's no much literature available. Now I could see that the professors' knowledge in this aspect, particularly our application in aerospace, is enough. Enough. Well, last time we had a discussion with so-called Rakesh Sharma last Sunday. So all are talking about the material only, and everywhere, wherever we go, even I met a what do you call it, ophthalmologist. He also talks about material only. You go to all specialists, and particularly ortho, they also talk about material. Dentist, needless to ask, dentist, their survival is with the smart materials. Although the cost for equipping or starting up what do you call it, this so-called clinic is very costly, but till then, that materials are helping them very easily. It is helping, not like those days. Those days you have to go to China Bazaar in Madras to meet a dentist. Now all dentists are available, latest material. However, coming to my our subject, I have only one word. Right. It's like a golden opportunity. Professor is with us, Professor Rudy. Please, all the students, have a patience. Understand the time. Don't worry the time. You are worry about your career. Listen. I hope this is more than sufficient for me to talk. I don't want to take much of this time. I myself want to hear more from Professor Reddy sir. Thank you, sir, for having accepted our invitation. I wish it should be much fruitful for one and all, particularly not only for the student fraternity, but also person like me will be I'll be enthralled and very keenly waiting for professor's speech. Thank you, the organizer. I thank once again the management, my learned professor, my battalion for their full support. Battalion includes, I mean, my student friends. Thank you, one and all. Let it be a fruitful session. Mic over to Godwin.
Thank you, sir, for the address. Chief guest introduction. Chief guest of the day, Dr. Murthy Chavali, Professor of Analytical Chemistry and Nanotechnology, received his MSc in Chemistry from Jawaharlal Nehru Technological University, India, and PhD Tech from Technische Universität Wien, Austria in Analytical Chemistry, postdoctoral fellow in USA, Japan as JSPS and VBL fellow, and Taiwan NSC fellow. To date, he received 41 international travel grants fellowships for visiting abroad and visited around 52 countries. Also represented India, Taiwan, Japan, Austria, etc. Professor Dr. Murthy Chavali has over 24 years of research experience and 19 years of teaching experience. Also established 8 research laboratories. Recently, he established a nano characterization laboratory, one of the best labs worth 400 lakhs around with BTech, MTech, and PhD programs in analytical chemistry and nanotechnology. And he guided over 149 students, of which 18 PhDs, 3 MPhils, 5 PDFs, and sent nearly 159 students abroad with full scholarship. In the year 2014, he was selected to the top 40 analytical scientists of the world by the survey conducted by American Magazine, and also received 4 award certificates from elsewhere for his outstanding reviewing. He published his research works in journal of high repute with high impact factor related to all types of sensors, nanomaterials, nanopolymer composites, nanothin films, and published over 216 articles in various international and national journals. He presented his work at 208 international and national seminars, symposia, conference, workshops, responsible over 150 technical reports and 56 books written, and delivered around 192 initiative talks, both at national and international levels, contributed towards 10 patents as well. Projects: principal, co-principal investigator, collaborator, reviewer of several national DST fast track, UGC, CSIR, DRDO, and international projects DST International. In the last 10 years in India, he has completed 7 research projects worth rupees 3.85 crores, and in total, he completed 47 national and international R&D projects worth rupees 68.94 crores. Currently, he is Director of PG Studies, SPRM College, Nagaram, Andhra Pradesh, Chief Scientist, NTRC, MCETRC, India, Visiting Research Professor, USA, Japan, and Austria, Visiting Professor, Malaysia, Taiwan, and KSA, Visiting Research Scientist, NSC, Taiwan, Visiting Research Fellow, European Consortium, EUC, Consultant Industrial Nanotech, R&D, and Consultant Higher Education Abroad. Now, I invite Chief Guest of the Day, Professor Dr. Murthy Chavali, Professor of Analytical Chemistry and Nanotechnology, to address the gathering. So, welcome, sir.
Yes. Can you see the screen, please?
Yes, Professor.
Can you read everything?
Screen we couldn't see, Professor.
Okay. Thank you, Professor, for giving me a nice introduction and also the kind words for your director and HOD. And at the outset, I should thank Mr. Kaushik for giving me this opportunity to share a few of my experiences in smart materials towards industrial applications. I try to converge. I'm not an aeronautical person or an aerospace person, but I'm a materials person where I work on different materials for sensors and sensing devices, sensing structures, both at the smart level, intelligent level, etc., etc. Coming from a chemistry background, we prefer to work on materials and nanotechnology at the nanoscale and microscale levels. And once again, at the outset, I thank the organizers for giving me this opportunity to talk about smart materials for aeronautical and aerospace applications. This lecture is going to be divided into, as the title says, smart materials is one section and applications is one section. I try to converge most of the applications, selective applications towards student understanding, and with the text of smart materials for most of the MTech and BTech students. And at the same time, I try to give why these materials are promising because of the market trends. And also I start this particular lecture with some of my research areas. These are some of the areas where I'm presently working on. Number 5 is applied nanotechnology, which we call it as applied nanotechnology because most of the applications we start with scratch to application level. So different areas where we are working presently is in applied nanotechnology. And in addition, we are also working on different fields in mechanical engineering, electronic and communication engineering, and biotechnology. And we publish most of these results in high-indexed journals. And over the past 10 to 15 years, these are some of the selective key technologies developed in various fields, starting from nanotechnology, analytical chemistry, chemical metrology, and smart materials, hybrids, metal oxide, dual metal oxide, triple metal oxide, etc., etc. And these are some of the list of the publications that we have done over a period of time, and most
Excuse me, sir.
highly published papers are basically coming from last.
Excuse me, sir.
Yes, go ahead.
Sir, your skin is not visible, sir.
Yeah, that's what I was asking. Okay, let me start once again. Is it visible now?
No, sir.
How about now?
No, sir. It's
One
not
second.
showing.
How about now?
Yes, sir.
Yes, sir.
Can you
It's
see?
only getting.
Yes,
That
sir.
No,
is
sir.
visible, sir.
Okay.
It is visible now.
Yes, sir.
Visible, sir. Okay.
Okay, I've finished 3 or 4 slides already. I just flip through for your understanding since you did not see. And this is a typical work my team does in the period of last 10 years. Coming to the exact lecture, what we are trying to talk about or listen to. Coming to the history of materials, it started from Neolithic era where metals are the topmost materials, and the properties have been decreased, usage has been decreased over a period of time until it gained some importance in 18th and 19th century, which is ancient age, from where different types of new alloys, polymer composites, elastomers, and ceramics and glasses are coming. But the actual true work of this particular hybrid polymeric materials, elastomers, and ceramics have started in the early 21st century with CFRPs and GFRPs. And what exactly they are useful for or going to be seen in the next coming slide. I'll try to give some of the interesting examples for materials. For example, if you see the first one, Vincent van Gogh Rose Garage cycle path. The first picture which says is a night picture which has been taken in Eindhoven city, where materials have been patterned in such a way for a cycle path for the cyclist to understand, and you don't need any additional energy sources for this to lit upon. So this is one typical advantage of this smart materials patterning on the soil or the concrete, where cyclists can see the path without using any other additional energy sources. And also you have a lotus dome and lily rome. And the third one is the most important thing. Using bioluminescent materials of animals, scientists from Taiwan, they have introduced this bioluminescence into plants. Exactly at the night time, these plants used to shine through different colors of lights. That means there is no requirement for these streets to have street lights. This itself gives a lucrative appearance, and at the same time, these are highly useful and energy saving. So such type of smart materials are available as on today. And in some other Western world, they have glowing infrastructure. The buildings on either side of the road have been patterned, colored or coated with the different types of material that fluoresce. So you literally don't need any directions, or it doesn't need any of the materials to lit up on the street. So all these types of societal applications are also useful in addition to technical and professional applications of these particular smart materials. And for example, if you talk about any of the materials, advanced material means we simply think about electronic materials or superconducting materials. In addition to that, there are a lot of materials which are biodegradable, nanomaterials, composites. Composites are nothing but a mixture of one or two materials together to have both the properties engulfed into one material. Smart materials, which we are going to see right now. And with the advent of development of nanotechnology and artificial intelligence, these smart materials are going to grow into different applications and develop new functionalities with these smart materials, and some of them got into next 2-3 levels of applications, and beyond that they used to call these materials as future materials. For example, if you want to convert materials into smart materials, they need to address some of the smart technologies like sensing and activating together, the control, self-detect, self-diagnosing, self-heal, etc., etc. Now we are in the stage of smart materials, and they are being deployed. I'll also try to touch upon some of the smart nanomaterials, since our field is materials working in nanoscale. So why not I try to give some of the market trends and what are the usefulness of smart materials, and I'll conclude with some of the future materials. And what do you mean by smartness? Smartness is a specific application which has to be precisely measurable, and it can be achieved in no time. Plus, it should be realistic, means it has to measure in the real world samples, and it should be also be able to measure within the time period. And a sensor or a controller or an actuator, all three have to be controlled by one unit by distributing the data communications, transmissions, and power, etc. between them. And everything has to be controlled. But if you talk about the materials, we know what the materials are. But at the same time, if we want to talk about the smartness, a smart material or device, it has to sense and it has to be adaptive to environment, and at the same time it has to control and it has to decide to act upon as and when it is necessary. So smartness lies at the center of all these contours. So smartness is nothing but adaptive, sensory, active, and controlled. For example, we can see in terms of aeronautical engineering application, you can see smart materials working as a sensor, screen printed and embedded between two laminates within the fuselage of an aircraft. This is one of the best examples where the smart material can be used upon in aeronautical or aerospace industry. And also, most of people are getting confused with aeronautical and aerospace and astronautical. Aeronautical is nothing but branch of science. It deals with design, production, and maintenance. Aerospace enters into the atmosphere, but it really works in the space as well, but not really with atmospheric conditions. Astronautical is the one which works in the science and technology of the spacecraft and launch vehicles. With this difference, we can see the smart materials are extended from aeronautical to aerospace to astronautical. That means they have a lot of applications, a lot of hindrances to maintain or to be with, like temperature changes, pressure changes, material hindrances, toughness, strength, lightness, etc., etc. So these are vividly applied in most of the areas. Once, if you talk of aircraft where there is a lot of load and lift which is required for the aircraft, so they need a metal which is high strength and it should be lightweight. So in the initial stage, it has been decided to go with aluminum, where 25% of aluminum is consumed in the transportation industry, which is because one-third weight of the steel, and also it is highly fuel efficient because of less weight, and also highly resistant to corrosion. And at the same time, these have been evolved into different alloys like aero aluminum grades, aircraft grade aluminum, etc., like 2024, 7075, 6061, etc. So aluminum is the primemost material, and their alloys and their composites are coming up as smart materials. So by 2025, it is estimated that it is going to be double to 80 million metric tons of usage of aluminum. But this is going to be dethroned. Dethroned means aluminum is going to be replaced by thermoplastics, because of aluminum itself is a lighter material, but at the same time it is 10 times lighter than the metal. And polymer composites which are coming up both are transparent, lightweight, with high strength. Composites are exceptionally strong. So they are trying to dethrone or combine with aluminum metal oxides, metal composites, and this is going to result in weight loss of 60%. That means you are going to earn your fuel costs, you are going to have a longer lifetime, extended flight range, and this plastics and composites are the primary secret for aircraft fuel efficiency. And among these, two high powerhouse polymers that are being used in aircraft industry are PEEK, polyether ether ketone, and ULTEM, which is a part of PEI. These are the two materials that are trying to replace or dethrone aluminum from aerospace industry. And coming to smart materials, this was started way back in 1932 with the accent of materials transformation of gold and cadmium, which is nothing but 916 kdm gold jewelry, what we use in our daily life, which means where cadmium is a low melting point, with which when you evaporate or when you melt this gold, cadmium is completely evaporated and you can get the high purity gold immediately. This is the first type of smart materials where to try to avoid amalgamate between gold and cadmium. And in 1938, the invention of phase transformation in brass, and in 62, nitinol, which is a very famous shape memory alloy for used in aerospace industries. And with this, Boeing in 2009 started with carbon fiber plastics. Complete wings and fuselage has been completely made of these particular carbon fiber plastics to reduce cost and at the same time increase the flight range. So these smart materials initially they were not understood. They were typically placed in a wide group of different substances because of one or more properties and advanced properties which are not clearly understood. And these materials react quickly to a stimulus, and at the same time they are also reversible. So most of the properties, since they kept in a wide group of different substances, they prefer to sense, activate, control, decide upon, and you can think at this particular level if you implement smart nanomaterials, I mean nanotechnology embedded into smart materials and artificial intelligence, they typically act like a nanobots. So this type of evolution has come up, and this has been understood because of these properties, and they are widely used as shock absorbers, self-healing materials, self-collective materials, self-controlling materials, etc., etc. Since these materials sense and react, they can be called as intelligent and responsive materials. And these materials can be designed. So some of the people, they call it as designer materials, because you can tune these materials to your requirement of application, whether it is engineering, whatever engineering it is, it's electronic, mechanical, or nanoscale fluidics, or whatever it is. And these can respond to the external stimulus, and they can change the shape, color, size, and stimulus can be light, heat, or magnetic field, or chemical, or whatever it is. So these can typically act as an intelligent and responsive material because they can sense and react together. And these are multifunctional because they can do one or two functions at the same time, and sometimes they are trying to handle 3-4 types of functions at the same time. They can adapt to environmental changes immediately. So because of responsiveness, they can be called as responsive materials. And these responsive materials, they can react immediately, so they are called as active materials because they react to the environments and react to the sensor phenomena and react to the material or application of our interest. Or it would be more accurate to call them as reactive materials. And subsequently, they evolved into, with the application of nanotechnology, smart nanomaterials. For example, if you try to represent, because these were not classified before, and these pictures were taken as an illustrative representation for smart materials, they are in different wide groups. For example, if there is a mechanical shock, they put them in the piezoelectric category. If there is a change in this particular smart material because of voltage, they call them as electro-responsive. Based on acidity or pH, they call them pH responsive. Based on magnetic, they call them as magnetic responsive. And for heat, thermal, and enzymatic and redox, both oxidation and redox schemes. But these redox and enzymatic are not in aerospace applications, but the rest of them see profound applications in the field of aerospace aeronautical engineering. And you can see almost 6 varieties or 7 varieties. And typically, if you want to represent all the smart materials in one category, here you have seen balls with 2 types of colors in different halves. And you have spoon-like structures. When you apply this external stimulus, they change into, they arrange orderly with a similar color on the top and other color on the negative side, on the bottom side. And they tilt, the spoons, they tilt because of external stimuli. And at the same time, these are reversible. Once the stimulus has been removed, these balls go back to normal station and they get back to the normal shape in which they are existing before the application of the stimulus. So these are some of the materials that they can be reversible. At the same time, they can sense, they can react, they can alert, they can give security warnings, etc., etc. And this has been started way back by a Brian company, where they have created a tape-like material, so thin material, but it is as strong as steel. With this, the properties have been embedded into materials, and they have developed different types of designer material to have a quick response. And that's how these materials have been evolved. And if you talk about modern materials, for ages we have paper, wood, stone, metals, and concrete, aluminum, steel are most modern materials. In addition to that, via Smartness, we have new materials like graphene, metal foams, lightest possible material, and liquid crystal displays, nanomaterials, modern materials can be used along with smart material, because these modern materials like graphene, metal forms, and nanomaterials can combine with other materials so that they can become smart nanomaterials, because these are all in the nanoscale rather than the macro scale phenomena. And what are the benefits with these smart materials? They are definitely lighter material because they use peak and ultim. They lower fuel costs, they reduce emissions, and extended flight ranges are very much possible. They have security element. They can warn. They can check the security, and they have products with new design. They have multifunctionality. They have potential for new function development, and they can also be utilized in quality control. And more or less, they are transparent. Some of them are transparent, so you can see through these particular materials, and you can understand the possible methods that are being applied within these particular devices, etc., etc. The primary objective of this is to have a specific performance to be enhanced. With that particular goal, they can have new capabilities, they can perform well with the smart materials. For this particular reason, they also interact with the environment, with the people, and without the need for them, they can be connected to the electrical supplies. They can work upon themselves. So these are highly responsive, intelligent materials. They can be designed in a less complicated way, and they can be more robust. In addition to the aerospace industry, these can be applied in medical, construction, electronics, what else and whatnot. And finally, with all these things put together, they were classified into 5 major categories initially. Because of their adaptiveness, they can work as actuators and sensors, and they can be controlled for their mechanical actions. With all these applications, these smart materials attracted research option by different scientists, and they can be grown, and slowly they can be replaced with the traditional technology what we have right now. And they also have a potential for new function development. If you see here, this is a magneto-responsive material. Once the magnetic materials or nanomaterials are introduced, they form into a straight line. That means the rheology is being altered, magneto-rheological materials. So this sees a wide variety of applications, blocking the unwanted things. It can be used in filtration, biomedical, it can be used in fuels, so on and so forth. Such is the type of application that they're going to foresee as a future material. Future material in the sense smart nanomaterials or smart future materials, whatever it is. And coming to the functionals, as we discussed, it has dual functions like that of hybrid materials, and at the same time, it also has multiple functions, not just 1, 2, or even 3, even more. The best way of applying this is saying this is the nitinol PZT materials as a ceramics, where it can withstand mechanical deformations, and it can generate voltage, and it can also generate mechanical strain with the voltage, etc., etc. And composites, which are nothing but at least 2 different materials combined together to have desired property for that particular application. For example, glass fiber reinforced plastics or fiber composites are the best examples for functionality in aerospace industry. Suppose, since we talk about the categories of smart materials, we know what piezoelectric materials are, where the stress is applied, electrical charge is generated. When you apply electrical charge, this method, mechanical straining is occurred. And electrorheological fluids means the fluid viscosity, fluid parameters are being changed when you apply voltage. Magnetorestrictive materials means mechanical strain is the output when you apply the magnetic field. Shape memory alloys, heat is applied to get back to their original position or change into the shape. Temperature, pressure in optical fibers lead to change in electronic signals. Mechanical strain also lead to electrical signals, but temperature pressure is much more lesser than mechanical strain. So these optical fibers can able to detect ultra trace level gases. That means it can detect something in the order of parts per quadrillion, ppq, which means this has a very large evanescent wave region where our transducer can sense and it can detect based on these changes in nano electronic signal levels. So all these things are possible just by stimulus, and their responses can be measured as an actuator or a sensor or as a warning for the entire device or the system. So if you try to understand one simple thing, here in the center you have a stimulus. It can be humidity, magnetic field, temperature, light, or pH. Here you have different shapes. They are converted into different shapes. And these are reversible. At the same time, they are intelligent. Because of humidity, this can be swollen. Because of magnetic field, the temperature, they can change the shape. And because of light or pH chemical, this particular T-shaped thing can be self-assembled into a box-type structure by its own. So these things are because of the material that is being present in the original column. From here, it is transferred because of the external stimulus and then come back to a normal position as and when it is required. Such is the source of and function of this particular smart material. Again, they have been classifying based on property changing, means mechanochromics twist, and the output is going to be mechanochromic. Mechano is an action, which is a twist. A simple twist of this material converts themselves into chromic, means color variation is being occurred. And here we have classification of this particular smart materials in two varieties. Type 1 is property changing, type 2 is energy changing. And in energy changing, you have again two types. One based on electrical potential, and one is emission of light. This is typically electrical voltage production is piezoelectric. One of the best material example for this is barium titanate materials. What do you call is the kids' shoes where they light up on when they walk. Means mechanical stress is against this particular material, releases minor voltage and let the LEDs glow. So you have electric potential difference, and you have a minor electric voltage. And the same is the case in the case of photoluminescence or electroluminescence, thermoluminescence of fluorescent materials, photovoltaics, whatever it is. But these electroluminescent materials are further taken into two varieties, fluorescent and phosphorescent materials. Based on the time delay, they were classified into fluorescent and phosphorescent materials. Coming to the actual classifications, you have n number of classification, n number of materials. So typically they were placed in a wide group of different substances, which has no meaning at all. And finally, they were able to attain into different categories, or the 5 categories of piezoelectric materials, shape memory, chromoactive, magnetorheological, photoactive. Based on this typical nomenclature, you can identify what is the type of material, what is the input, what is the output. That you are going to understand by yourself. And as I said in the primary classification, they were classified based on the property change and energy change. Energy change based on their output, electric voltage or color. And this has been further classified into passive system, active system, and a hybrid system, where they have two things in one. There is hybrid system, where they take outside help, external stimuli, internal stimuli, passive and active system. Or typically they have classified by another group of scientists as 5 or 6 categories. And the 6th category, which we have mentioned, is just others. Because we have so many types of materials here, it was all classified into 5 categories. The rest, which is left over, has been put in the category of others. The same can be explained in a different way, and these others can be a mix of these two properties, or mix of these two outputs, or mix of these 3. So this is a typical designing or a typical interaction with the smart materials to be able to perform as a smart materials with dual functionality or multiple functionality. The best example is the magnetic nanoparticles in the smart materials control the fluids. So we call it as magneto-restrictive materials or magnetorheological fluid. So all these things kept under others category. And another classification that they say about the smart materials is chromoactive materials, where color is activated with these materials, where the light active materials, which is photoactive materials, and simply put rest of the things where they change the shape of these particular materials that change shape. Thermochromic materials, which means heat is involved in changing the color, light is involved in changing the color, Water is involved in changing the color, which is hydrochromic. Voltage is involved in changing the color, which is electrochromic. And as I said, light involves in luminescent material. Electroluminescent, photoluminescent, fluorescence will come in this particular, where the intense fluorescence is because of this electroluminescence. And photoluminescence are the materials which emit light radiation even after the initial source has been removed. And in materials that change, that swell, that shape memory materials, self-healing materials, hydrogels, all these things come under materials that change shape. For example, if you take, as I said in the beginning, you can see the colors of these skates shows where you have different types of colors, different types of materials with the different LEDs. They activate the minor signal that is being generated while you walk, mechanical stress that is being exerted on this particular material, so that they emit this radiation, which without any, it is reversible, so it will gain once again from mechanical state to electrical voltage to strain, and strain to electrical voltage to mechanical strain, and so on and so forth. These will be working like forever. A mechanical stress is applied to a smart material that causes a small electrical change to generate, and this is the typical function of a cigarette lighter, which is a very good example, where the stress of the material generates minor voltage that lifts the cigarette. So these are such important materials called as physical piezoelectric materials. And the other type of materials are chemical sensitive or pH sensitive, where they can act upon food materials, where it can be treated as eatable, edible, or non-edible. Once they change the color, that means they are not edible. They have different materials, so this triggers the security alarm not to eat. And sometimes these materials, they swell upon, giving an indication that these are not good for edible purpose. So like this, you have chemicals changing their color, which is pH sensitive. These materials are called halochromic, and the other type of materials are called thermochromic, where heat is the one external stimulus that gives a warning or gives a color change phenomenon. For example, if you take cups, when warm, no color; when cold, they have a different color. And you have T-shirts where the ink is being loaded with the liquid crystals, and based on the body temperature, it lights upon two different colors. So all these materials have a specific function without any usage of external energy. Magneto-rheological materials, as I was telling before, MR fluids and so many materials, these functions are still not known, but they can be called as future smart materials because of their wide range of functions in shock absorbing, patterning, biomedical applications, and at the same ultra filtration techniques in dialysis and so many other things. They have enough number of applications that can be isolated, can be examined, and even evolved over a period of time. So this particular type of smart materials, which have function of magneto-rheological phenomenon, they call them as the future materials. Chromoactive material, which we have seen already in these particular slides, and you have halochromic, hydrochromic, photochromic, and these are the typical examples where you can see the change in color before and after the external stimulus, where you have input and output, and all these things can be used for societal applications or funny applications, or even industrial applications, or even in aerospace security warnings, or so many other things. So these particular materials can be utilized in different ways based on their strength and weight. And these are also some of the examples for photochromic materials, where sunglasses are the typical examples. Once you have a excess UV light, the color of this particular glass is going to change, become darker. And the same is the case in case of thermochromic pigments, where you can see the change in color of this spoon, and at the same time the cup. Cup changed to orange when it is warm. Spoon became pale in case of warmer temperature. The colder part is having the same type of color with the original one. So you have shape memory alloys, shape memory polymers, shape memory alloys. All these things can be utilized based on their stimulus, based on external stimulus, based on their change, in robotics, automation, etc., etc. Electrochromic application is a part of photochromic, where it becomes dark when you're exposed to UV radiation. Typically, this has been used for window panels, and also they can be used in day-to-day transportation trains in metro rails, where they automatically turn off excess radiation that is coming into the compartment through darkening these window panels. And they have a lot of applications, not just in this case, but in case of industrial surface phenomena, where they can be reduced or connected with different things. All these things can be used for energy generation, and without energy generation as well. Photoactive materials, as I said, you have electroluminescent materials, photoluminescent materials, and you can see the brightness of the fluorescent materials over this figure. And some are being fluoresced even in the absence of initial light external stimulus. So these materials are called as phosphorescence materials. These are all highly useful. Doesn't need any external source, and we can go through all these applications just because of stimulus. And more important things are these are reversible, and they can be employed in so many other things. In case of material that change shape, one of the best example is hydrogels, where they absorb 1,000 times of water beyond their weight. Self-healing materials, I'm going to have 2 or 3 slides on this. Self-healing materials, shape memory materials, and materials that change volume, which are hydrogels. And sometimes they can exceed 500 times or even 1,000 times. So with these shape-changing elements, for example, if you take shape memory alloys, it has an original shape. When you apply some heat, it changes shape, and when you returns to original shape, then it is in the cooler stage. And the same is the case can be explained here. But this particular change in shape because of the heat that is given to this particular material, it shrinks its length. Shrinking in the sense dragging the other side. That means you have a function of lifting when it is shrinking without usage of any other energy. So these smart materials can be used to lift the materials, and because of shrinking, they can use these wires in its robotic form. Shrinking is nothing but pulling down the phalanges within the robotic arm. That means you are literally making shape memory alloys within the robot to work upon, to catch upon any of the components as the wire becomes shorter. Because the wire becoming shorter is not known to anybody, but the actual function is literally seen as an output. The shortening can be used to control the robotic arm. And the same is the case in case of other magnetic shaped memory alloys, where these applications are in thousands and not yet unleashed by most of these particular materials. So they call these particular materials as future materials. Hydrogel can absorb up to, depending on the composition and structure, 500 to 1,000 times, and it can see a release of this absorbed water from these hydrogels, either by changing temperature or pH. So it has a lot of applications in artificial muscles, hair gel, nappies, magic, expanding snow, and even granules to help the soil. And these materials are usually used in desertification conditions. So another important thing is grease. You know the function of a grease, which is sticky, viscous gel, which lubricates most of the thing. But the smart gel has a different functionality in addition to the existing functionality. A novel application is wound up the motors and to provide uniform speed and at the same time torque output. By this, you can increase the lifetime of your machine. So this is smart gel is being applied in most of the devices, industries, in a tiny amount, so that the frictional between surface is reduced and everything has been enhanced. For example, if you see specifically about smart materials in aero industry, typically you have 50% of advanced composites, you have titanium, so strength, aluminum, steel, and other materials in a typical aircraft. But over a period of time, now this is the present stage is going to be 797 Dreamliner, where the composites have taken part most of the areas and reducing them with aluminum and other titanium materials as and where just required. So typically they reduce the weight and they increase the flight range. They save on fuels, etc., etc. Even with the advent of materials like shape memory alloys, piezoelectric materials, CFRPs, shape memory polymers, shape memory materials. I mean, typically put together SMA and SMP as SMM in aeronautical application. But typically, with all these functions, what we need is we need to reduce the weight. We need high strength materials with reduced weight. We need high temperature materials because there is a lot of change in temperature from liftoff and to flight pattern, flight path, and to land. Temperature material, low temperature material, high temperature material. If you try to use on these types of materials as and we progress, you need to put on the weight and your extended flight range is going to be reduced. So you need to have all these particular properties filled in one material as a multifunctional smart material. So we are in search of different types of materials, coatings, hybrids, with different types of proportions and compositions. So nanotechnology coming to the aid with different types of strength. I'll try to tell you on the next slide why these nanotubes are being used as one of the materials, because they have a distinct properties, specific uses, and because of these specific uses and properties, the value of this particular market is skyrocketing right now. Why? Because they have extreme properties like so and so forth mentioned in density, size, tensile strength. If you see some of them as highlighted here with a star, for example, single wall nanotube, the size is going to be 0.6 to 1.8 nanometer. And in the E-beam, it is only 50 nanometers wide. If you take temperature stability, they have 2800 degrees centigrade temperature stability. Metal wires are only up to 600 to 1000 degrees centigrade. If you have this polymer composites with metal composites, you can increase the temperature, but at the same time strength also increase. But if you replace these metals with carbon nanotubes, you are going to have increased temperatures, you are going to have increased tensile strength, which is compared to 45 billion Pascal compared to high strength steel, which is only 2 billion Pascals. Current carrying capacity, highly conductive materials in 1 billion amps, and copper wires burn out at about 1 million ampere per square centimeter. So all these properties extend these materials as one of the additives for smart materials, better than metal composites, metal polymer composites. And also you have novel wonder material graphene. This also higher strength than carbon nanotubes, and at the same time, because of this zero band gap, they can be flexible, they can be revolutionized. Different materials, even as a smart materials, they can be employed along with the strength. And if you see, they have high thermal electrical conductivity, ultra lightweight. They have the ability to self-repair, like self-healing materials, composites. They are not vulnerable to overheating. They are 200 times stronger than steel, unlike carbon nanotubes, which are 10 times stronger than steel. So these are also another wonderful smart materials. When combined with different materials, they act upon themselves and they can give different. Because of these properties, the market trends have been grown with a CAGR as 30% through 2025. And this global smart materials market is close to 98.2 billion or 100 billion, which is going to reach by 2025. And most of this particular market is North America and Europe. But in Asia, Pacific region, India, China, Singapore are coming up with this smart materials market because of advent of applications, new formulations, new applications, new potential functional developments in the smart materials. They are going to come up. And these, over a period of decade, they can be classified further based on the product, end user, and the region. Region, of course, we have discussed already. North America and Europe are on the top. And by product, it depends on different types of application and the end user based on the cost. Compound annual growth rate is just 13%, smart material. And you can see this smart materials, once you enhance this to smart nanomaterials, this CAGR 13% is going to exponentially raise, and you are going to see in the coming slides. And if you see this particular market from 18 to 26, you have very large production in North America, and they stand as North America, Europe, Asia, Middle East and Africa, and Latin America. This is the range for aerospace materials, smart materials by 2026. And in most cases, these are the materials that are giving a lot of dividends in terms of dollars. Piezoelectric, shape memory, electrorestrictive, electrochromic are the last, and others, different types of materials put together, were placed in the seventh cadre. And this is going to be through increasing market demand until 2025. And coming to the last section of our applications, we have several applications. In general, if you talk man-made composite materials, or which is very well known to most of the people because of the strength and stiffness, and at the same time they are also very brittle. That's why we need to include these nanotubes and nanomaterials and graphene nanosheets into this polymer matrix so that they can attain metal-like properties, but they have some of the properties which is very close to polymer composites, and at the same time they can also use some of the ceramics, smart ceramic materials to control high vibration, mechanical shock, and temperature variation. Ceramics are the best materials for controlling high temperatures, and piezoelectric and dielectric materials can be used as gyroscopes and accelerometers. And at the same time, one of the most prior ambition or objective of any of these particular aerospace and aeronautical industry is safety, reliability. So they need to have intelligent and robust materials to reduce the noise, vibration, and predict to have a textbook path for these particular materials. At the same time, they reduce maintenance costs. They get back their lost profits in terms of cancellation delays, extend the profits in terms of additional extended efficiency, and cut down the costs of fuel costs. So smart materials are always looks very promising. They are reliable, cost effective, no doubt about it. So this has been used specifically in the defense, multi-purpose, and also aerospace industry because they are highly adaptive, highly critical for many of the functions, and so they are being used in extreme accuracy, task ordnance, exacto, as a materials for bulletproofs, and also by DARPA, which is Defense Advanced Research Projects Agency, where they fund mostly on smart materials, smart sensors, smart structures, smart actuators. And this smart materials, they just revolutionize even the weapons for manufacturing used by aircraft. So overall, these materials are useful for high performance levels. At the same time, these are still in the stage of development for different functions. One of the best and important thing is to have integration sensor to monitor structural health of this fuselage and wings. And for this, as most of you know, because this has been used over a period of time for carbon nanofibers, used by carbon nanofibers, glass reinforced materials, and also they have lot of sensors into the wings where they measure the wind speed, they measure the turbulence, mechanical shock, lift-off parameters, so on and so forth, and at the same time temperature, pressure, and turbulence, etc., etc. All these things are related one way or the other to structural health monitoring. And in this, they are also trying to have different nanomaterials into them to stabilize, but still, this is still under development, where they have a lot of works published on this. I'm not going to go into those details because it is going to take a lot of time. And coming to the sensors and actuators, where these materials, piezoelectric materials, they act as both as sensors and actuators. In case of piezoelectric materials, where they act as sensors for high temperature variation, high temperature variations, high pressure, high radiation, high vacuum content. All these things can be used just by a smart material to monitor by changing the way they react to external stimulus. The same thing, they can also be controlled as a piezoelectric actuator just by counteracting the flutter phenomenon that may occur during the flight of the airplane. So typically this is one example for a dual function of a smart material where they act as a sensor, actuator, and this can be a multifunctional smart material because they control, they distribute, they transmit power between these two, and etc. by doing 5 or 6. So these materials can be considered as multifunctional smart materials, which are nothing but piezoelectric material. And the most important thing is morphing of structures, which is required for aircraft performance. Morphing wing has attracted a lot of attention over a period of time in the last decade because of its advantage to lift the drag ratio and at the same time flight performance. And for this, they just use shape-changing material like shape memory material or shape memory polymer, shape memory alloy. And this morphing can be done in 3 ways, 3 categories: large, medium, and small. Whatever it is, the ultimate goal is to have a commercial or military aircraft using smart material technology for their aircraft performance. These are some of the advantages of morphing in these particular aircraft mechanisms. So all these things can be possible by utilizing different types of smart materials. And in case of performance, and this is one of the most important things which has attracted so many things. You want an aircraft with ultra fast speeds. For example, defense sector, DARPA is looking into it, Exacto is looking into it, and at the same time, high speeds require promising materials because of friction with air, friction with temperature. For example, if you have a missile or a plane which is going at high speeds in stratospheres or atmospheres, whatever it is, the wind speed is more, and you need to counter so many things: turbulence, vibration, acoustics, shape control, multifunctional smart structure, morphing, and your antennas may not work at that particular speeds because it will not be able to detect the signal, incoming signal, and it cannot transmit the signal from one aircraft to the other to communicate with the other. So all these things are possible. So the best important solution for this is to have smart structures evolved in a different way, take their own decision, unmanned aircraft. So all these things are possible only with enhanced smart structure, means smart structures, smart materials with enhanced power, like smart nanomaterials, controlled by artificial intelligence, so that it takes its own decisions and it emanates its own signals through smart antennas, etc., etc. So the solved problems are going to be multiplied when you change specific set of parameters for these aircrafts in terms of performance. The same aircraft which is going at 800 kilometers per hour, if you want to change it to beyond Mach 1 or Mach 2 speeds, you need to change most of your materials, and all these things will not work at that particular speed. You need to have stealth reflector, so that all these particular things are very much possible. So US country is going to come up with a new aircraft for passenger aircraft, which is called as Antipode, which has a speed set at 1600 miles per hour. That means 25,000 kilometers per hour, which means you can reach New York to London by 25 minutes and London to New Zealand in 30 minutes. And this particular aircraft at this speeds, you need a different set of materials, and which can have very, very high, probably nanochips and graphene-based nano smart materials are to be required to be used. And this is going to come up. At the most, the fastest aircraft is Tupolev, which has 1.97, not the Concorde. Not to mistake, Concorde is the fastest one. Better than Concorde, you have Tupolev 144, which is Mach 1.97. And at the same time, commercial jets like defense aircraft like hypersonic aircraft X-43A, SR-72, they have 9 and 5 speeds, max speeds. And at the same time, you also have magnetic smart materials, which I said you have a lot of things that are being used by actuator technology, where they implemented in 2007. where the idea is to reduce the vibration produced by the aircraft and the lightweight. For this, they use magnetic smart materials with a magnetostructure and coil and a spring, where the precise change in length with the high force and lightweight makes magnetic smart materials as excellent component for building actuators. So all these things, lightweight materials in terms of composites. If you see over a period of time, for example, in 747 Boeing, 81% of aluminum has been reduced to almost 20% of aluminum by 787. This is in 2009. So all these things are taken into play, and you have different types of material that are being used in while it transformed from 747, 767, 757, 788, and the latest one is 797, which is new mid-size airplane where it has very less amount of metal and it has more amount of composites. And the new one that is going to come up is a Boeing Sonic Cruiser. Is a typical schematic view for commercial airliner. And the new one, which is going to come up by 2025, is Boeing Yellowstone Project Y1, Y2, Y3. 3 planes are going to come up, and this also has better than supersonic speeds, and people say it is more than 2 Mach, 2.0 Mach for a commercial airliner, which means you can see you can expect different types of material that are going to gain. And if you take Airbus, it also has 53% composites in 350, and in the other case, they use 20% of composites in case of A380. And metal composites are used in certain areas to reduce the metal and substitute with the type of polymer only because of its elasticity, ductility, and resistance to elevated temperature. Metals are the one best example which are better than polymer metal matrix composites and use metal in their composites. So these are the types of material that are being used for various applications in aerospace, aeronautical, defense, and transport phenomena. So it also have several types. For example, if you take Boeing 777 launched in 2000, they have 11% of composites, and in 787 you have 50% composites launched in 2007. So one of the best thing about these is corrosion resistance, design flexibility. You can design these materials, understand their performance, simulated performances, and then they can be used. And also flight accidents, you need a lot of fire resistant composites. In this case, they are using as an interior glass reinforced phenolic composites to 90% in aircraft cabin, and at the same time carbon reinforced composites for outside material like fuselage, wing, and tail fin, which is also 90%. So all these things react towards only one thing. One is performance, the second one is the safety. Self-healing composites. If you see a crack in the wing or any other areas, these materials being present inside, they have non-polymerized materials, and once you have a crack passing through a monomer, the monomer breaks and this polymer mixes with the hardener, and then it fills up the gap and polymerizes automatically. And these self-healing composites have 2 types of approaches. One is extrinsic, the other one is intrinsic. So with this, you make these materials smart, and the crack is being healed, and it can be used in fuselage, it can be used as a coatings, and sometimes these are being used, sometimes because these are not suitable for high temperature materials, but sometimes some of the areas on the outer side they are being used. For example, if you use ionic liquid polymer composites, this is a new type of materials available by the chemists, where these are chemically, electrochemically, thermally stable. Means beyond the range of composites, if you use these ionic liquids, they are chemically, electrochemically, thermally stable, and they are non-flammable and non-volatile. So extremely useful, not just in aero industry, but in biomedicine, energy, actuators, sensors, and environment. So these are completely utilized as a smart materials in combination, and these can become, they work at room temperature, they can become a novel class of chemical composition. As we discussed, interiors and exteriors, this can also be used as aerospace textiles, reactive glass, which is a smart glass where it can be controlled on its own. It takes the decision based on the input of external stimulus and converts as per the output stimulus. And at the same time, they can also have a lot of applications, lightweight blinds, curtains, etc. can be done with this. And obnoxious, toxic gases, all these things can be controlled, designed, delivered on its own by these nano smart materials. And we also have application in the high entropy alloy materials as amorphous aluminum alloy as a reinforcement. As landing gear is one of the most important and essential part, and it is always subject to power of the landing effect and weight of the indirectly it affects the weight of the aircraft. So it's most important one. It needs to have no concerns, no compromise on this particular. So you need to have a landing gear that supports and allows aircraft to fly, take off, land, and the most essential and important one. Such things should be error-free, and if it is smart enough, that can be controlled very easily, and it would be a wonderful thing. And other applications for this is it's a wow effect based on all the stimulus, reversibility. They call this as a wow effect, and at the same time, security is one of the important things in the safety of the plane. In warning the sensors by changing the color, changing the shape, causing a depression, causing elevation in temperature, changing the color because of the temperature, and in particular, thermochromics are used as a temperature electric current is not needed for these particular materials so that it acts upon their own. So these provide new designs. And another important thing is the smart gel. Usually one of the smart material respond to one type of stimulus, but the smart gel has different stimuli like light, magnetic, pH, temperature, electrical, and mechanical. This is one type of smart material which has profound number of stimuli which acts upon. So this can be responded. There is no chance of error, but at the same time, this responds to every type of external stimulus so that the change is countered, alerted, and stimulus will alter the polymer that makes more or less hydrophilic. So it can be employed in wet conditions as well, either outside or inside the plane for different applications. I'm going to skip this for the sake of students as there is no time. And coming to the future materials, most of the materials they are going to work upon transparent metals, biomimetic materials, self-healing metamaterials, air gel, biohydrometals, metallic foam. Number 7, metallic foams is going to be the most important one. Transparent metals are also going to be found in different potential applications. And some of the future materials, I'm going to show only few of the materials where synthetic spider web. This is stronger than steel by 5 times, even tougher than Kevlar, and at the same time, this is completely made of 98% of the material is water, and 2% is the chemical substance what they have, which is hydrophobic coating. This has been developed in South Korea and MIT in US, and at the same time, they can be used as a bulletproof materials. Shrill is another biodegradable plastic, which is typically made of chitosan from shrimp cells, and this material looks like completely transparent and like a carbohydrate found in krill shells. Harvard University people have developed this. Of course, you know the combination of potential uses of graphene and metamaterials. Metamaterials are those one where they arrange the composites and metals together for a different function. These are absolutely new class of compounds. Materials usually typically used as camouflage materials, antennas, etc., etc. Another one is cross-linked polymer. This is nothing to do with the aerospace industry, but typically this is called as a second skin. But this can be found some applications in stealth areas. If you improve this particular second skin to the next level, probably this can act as a skin, as a stealthy material for the aircraft, not to be visible or camouflage material, but still this has to be developed in into the next level to be used in aerospace or aeronautical industry. Coming to the last one, smart nanomaterials. This is just an idea where you can apply nano into the smart materials. It can see lot of enhanced applications. And one which I'm pointing out, the opportunities are vigorous and much more for smart nanomaterials in aviation and marine industry, typically a transportation industry. So these are also used in various places for smart materials, but the growth rate is comparatively higher than almost triple to that of smart materials, which is 13%. Now it is 34%, and the growth is going to be as such until 2025, compound annual growth rate. And this is going to be very lucrative till 2029. And again, the same is the case with the development and deployment of this particle in over the particular period, geographical region of the world. And to conclude, we have some of the publications, selective publications, where we use piezo materials for different applications over a period of time from 2012 to 2014, 2015. These are some of the publications that our team published in smart materials area. And we also have some of the publications in metamaterials, which is considered as future materials for electronic applications, and different smart nanomaterials for antenna purpose. And we have come up with 2-3 book chapters using these particular materials. In summary, these smart materials are still evolving. They are going to go to the next level or second next level as a smart materials instructors. And these objectives are very crucial for the production of smart materials, and they can be used as designer material to find profound functional future applications. They can be used as a graphic products, numerous applications still yet unknown to the aero industry. They can be developed into advanced materials beyond smart nanomaterials. They can also evolve into future nanomaterials. And main application of these 5, which are seeing present day aero industry application of thermochromic, hydrochromic, phosphorescent, photochromic, and electrochromic applications. With this, these smart materials have a long way to go in future and extend further beyond imagination, and they can go into the stage of nanobots with artificial intelligence and nanomaterials. And some of the materials that have been collected from these textbooks, which might be useful for the students to go through these references. And with this, I conclude by acknowledging all my team members and funding agencies and collaborators. And thank you for your patient hearing. Thank you. If you have any questions, you can ask me without any doubt. I hope I did not take much of your time.
On time, you took off and landed also, Professor. Yeah, wonderful session, Professor.
Thank you.
Even my close friend, Professor, 1975 of your category, done his MSc in chemistry, a friend of mine. I welcome Professor Krishnaraj sir is there. He's waiting right from 2:45 onwards. I thank Professor Krishnaraj sir to listen to you, sir. Really marvelous, sir. Marvelous. I'll be in touch with you, Professor. I'll be in touch with you to make not only my student but also myself a little smarter to know about how best we can use the control surfaces in making use of smart material, Professor.
Yes.
Thank you, Professor. Thank you.
Thank you.
Kaushik?
Kaushik sir, you can read the questions.
Yes, sir.
Yes, proceed.
Sorry, I will continue, sir. What are the smart nanomaterials that can be used for improving the fuel efficiency?
Can you repeat?
What are the smart nanomaterials that can be used for improving the fuel efficiency?
Oh, fuel efficiency. One particular thing is the viscosity of this particular materials can be altered now and then. Once you alter this viscosity now and then, there will be a control on the flow rates of these particular materials. So some of the people, they can use as rheological fluids, magneto-rheological smart materials, if you inject into this, they can work as an efficient materials, but still a lot of work is going on, especially in NASA, because I was there in NASA for 6 months in Jet Propulsion Laboratory, Ohio, where they started to use these particular materials almost 10 years back. I think they are further using these materials to have improved fuel efficiency.
Okay, sir. What are the applications of these materials in additive manufacturing of rocket engine components like injector nozzle?
No, engines, they don't have much applications because of high temperature. That's what I said in my slides. But in engines, outside coatings, they are trying to use these smart materials that most probably if metallic foams and other nanomaterials, if they come up, these can be employed in percentages in developing the engine also. Right now, we don't have much application inside the engine, only outside the engine.
Another question for you, sir.
Sure.
So, is there any future for aeronautical engineers in India? If so, please do give us some guides to lead our career in aeronautical engineering.
Hey, you have a wonderful career in aerospace, aeronautical, astronautical. You take anything. I mean, I'm confidently telling you, I'm an analytical chemist. Did my PhD in chemistry, but did my postdoc in combustion engineering. In mechanical engineering, working for Formula One engines and combustion rockets in Stanford and Ohio. So you can play your own part. There is a very lot more things to explore in this particular one section. I'm talking combustion. If you take other sections, you have too many applications. You have a very bright future doing this and researching in this particular field. Need not worry at all. Any other question?
So I think the questions are all.
Sir, thank you very much, sir. Murthy sir, it's almost like classroom for us. We have learned a lot, and we need all your help in future, as our director sir said, and certainly we need your guidance in future, sir.
Definitely, sir. Anytime, most welcome. I'll be available for you.
Thank you.
Thanks a lot. Thank you.
Yes, sir.
Okay, sir.
Yeah.
So thank you for giving a nice session and for answering the questions of the students. So now, as we come to the end of the session, I invite Mr. R. Kaushik Kumar, Assistant Professor of Aeronautical Engineering, to give the vote of thanks.
Yes, indeed, it's a pleasure for me to propose the vote of thanks, sir. First of all, I would like to convey my thanks to our management, our managing trustee and chairman, Dr. P. Krishnadas, sir, and CEO and Secretary, Dr. P. Krishnakumar, sir, and the management people, as well as our principal, beloved principal, sir, Dr. P. Manirasan, sir. In their absence, they have supported us to conduct this webinar organized in a very successful manner. Then I convey my thanks to Murthy, sir, the person who is very much knowledgeable in materials. Sir, really, you were just you were just shown us a ocean of knowledge in materials. So thank you very much, sir, for your wonderful timing and spending with us. Because I was spending time with Murthy, sir. I was calling him. I was very afraid of approaching him because sir is a very big person with a very big knowledge. So I was very hesitant to approach you first, but I feel right now that I have done a wonderful job. I have just did some achievement. I consider this organizing this webinar as one of my achievements, sir, by inviting you, such a wonderful person, to our institution. So I request you, sir, to visit our institution once you get time when you are coming to Coimbatore, please let us know, sir. We will like to take you to our campus. We will like to make you again more interactable with our students. We are not going to stop with this. We are going to extract more from your knowledge, sir. So thank you very much, sir, for giving your leisure time for us. And I thank our director, sir, Shankran, sir, and Dr. B.R. Sindhulkumar, sir, our HOD, for giving me this permission and as well as the support for this webinar. I thank my colleagues, my friends, and my student participants, faculty participants from other institutions as well as industry participants. So I thank everyone, and a special thanks to Anil Kumar, who is well known between me and Murthy sir, because Anil is my MTech classmate. He only gave sir's number, contact, and asked me to contact sir regarding this webinar. So thank you, Anil, and I thank Godwin for this MOC, and I thank everyone for participating and spending your time with us. Thank you very much. Thank you, sir.
I also thank Mr. Anil. I have not seen his. I have not seen him, Anil, but still I thank Anil, who's like a Tamil Anil, right? In the history of Ramayana, he made understanding bridge or between Tamil Nadu and what do you call it, Sri Lanka. I appreciate that Anil. At the same time, with my age, I have the privilege to give another degree to my professor Murthy. He is none other than a mobile library in nanotechnology and material science. Hats off for sincere delivery, professor.
Thank you for your words.
I'll be in touch with you. Sir. Thank you. Thank you. Have a good day, professor.
Thank you.
Have a good day. Nice.
Right,
Thank you, sir.
Thank you.
Thank you all for being with us and hope you all enjoyed the session. Thank you, everyone.
Yes. Though it is 4:30, 50, half-century students are there, really. I thank
Yes, sir.
Kaushik and Anil. Nice. Thank you, Anandal. Thank you, Professor. Professor Krishnaraj Subramaniam, sir. Krishnaraj, sir.
Thank you, sir.
I thank my Krishnaraj, sir. Professor, HOD Professor. I'm here
Yes, sir.
because of
Yes, sir.
Professor Krishnaraj.
Okay.
I should
Okay.
thank him.
Sir, thank you, sir.
He's also
Thank you.
Anil for me. He's also
Thank
Anil
you,
for
sir.
me.
Thank you.
Krishnaraj, sir. He's a
Thank you, sir.
person.
Thank you, sir. Thank you.
He's a person who handled aerospace material for
Okay.
BSB college. Nobody was to take that subject. So Sir only took aerospace material way back in somewhere in 2008. He took the subject.
Yes.
2007 or 8. Thank you, Professor. Thank you for sitting here, Professor.
Thank you, sir. Thank you, sir.
With your blessings, things are going on, Professor. Thank you.